Okay, kinetics and equilibrium. We're going to start with kinetics. This is nice and quick. Kinetics are how fast a chemical reaction actually happens. Okay, how fast does it occur? What's the rate? To speed up a chemical reaction, there's a few things you can do. You can increase the concentration of the reactants. I didn't spell concentration right. More particles in solution means there's more collisions. So that's ultimately what you're trying to do. That's collision theory, is to increase collisions and increase effective collisions. What's an effective collision? One that has enough energy to give it the activation energy. The activation energy is the energy to get over that bump. Okay? You can also increase the temperature. If you increase the temperature, the particles are moving faster. If they're moving faster, they're going to run into each other more and have more energy and therefore be more effective. You can also increase the surface area. Okay? That means using a powder or something that has more, like that's ground up, that has more surface area. More surface area means more area for collisions. You can dissolve things in water. I spelled dissolve wrong, forgive me. Aqueous things tend to react fastest. Solids, not as much, okay? So if you can dissolve it in water or some sort of salt solution, if you make it a solution, it'll react faster. Finally, you can add a catalyst. A catalyst speeds up a reaction by lowering the activation energy. That means that those collisions that are happening don't need as much energy. They can go a little bit less energy to get over the jump. Okay? That's how you speed up a reaction. Now, potential energy diagram. Let's use a different pen. Potential energy diagrams. They look like this. Up and over. These are your products. These are your reactants. Okay? Your activated complex is up here. If you are measuring it off this, if you're reading it, let's say your activated complex has energy of about 100, your reactants, let's say about 20, then your products can be, let's say 70. Okay? You won't always have numbers, and these arrows won't always be in the same place. They could be anywhere left to right. Okay? But the energy of your reactants you can read right off the graph is 20. It's from the bottom here at 0 up to the reactants. That's the energy of the reactants. NRG reactant. Energy of the product, same thing. 70, read it right off the graph. Okay? Your activated complex has an energy too. It's the highest energy point of the graph. It goes up to about 100 in this case. And those are the energies you can read right off the graph. Those are some arrows. They'll be from 0 on the bottom all the way to 3 different points on the curve. Now, the second thing that is important about these is delta H. Delta H is heat of reaction. And it's basically just the difference in energy between the products and the reactants. So delta H is the product energy minus the reactant energy. Okay? If it's exothermic, delta H is negative. If it's endothermic, delta H is positive. In this case, we have an endothermic reaction because the products, which have an energy of 70, minus the reactants, which have an energy of 20, give us a delta H of positive 50. Okay, and that means it's endothermic in this case. An exothermic reaction would look more like this. Okay, a step down. So this guy is exo. This guy is endo. Delta H on your graph, on your chart, is going to be between the products, forgive my uncalibrated smartboard, and the reactants. There's delta H. Okay, doesn't go all the way to the bottom, doesn't go all the way to the top. The last thing we need to talk about is activation energy. Activation energy is how much energy you have to give to the reactants and the products to form the other side. So if I'm going the forward reaction, I'm going reactants to products. how much more energy do these reactants need to get over this hurdle to form the activated complex? How much do I need to give them to activate it? It's from here up there, okay? So it's 10 minus 20, it's going to be about 80. So the activation energy of the forward reaction in this case is 80. I need to give my reactants 80 more joules of energy to get them to form the products, okay? Activation energy of the reverse reaction is going, reverse is products to reactants, and that's from the platform of the products up to the top of the activated complex. In this case, it'd be 70 to 100, which is 30, okay? The only thing that could ever be negative is delta H. Everything else is going to be positive, positive amounts of energy, okay? If you were to add a catalyst to this, a catalyst is going to lower the activation energy, and it's going to, but it's not going to change delta H, so it's going to kind of only affect right here. Your graph would change, but with that like black dotted line. That's going to affect my activation energies. They're going to be less, and it's going to affect the potential energy of my activated complex. It's not going to affect the potential energy of my products, my reactants, or my delta H. They remain untouched by a catalyst, okay? That's what you need to know about a potential energy diagram. Last but certainly not least is equilibrium. Okay, here's equilibrium. Here's my favorite equilibrium reaction. N2 plus 3H2 goes to 2NH3 plus energy. This is an exothermic reaction. Why is it exothermic? It's exothermic because energy is a product. Energy is produced. That means energy leaves, okay? All of these are gases, so I will put a little G there and a little G here, okay? Everything's a gas. Now, Le Chatelier's principle. Le Chatelier talks about how to shift the equilibrium from left to right, from products to reactants, and I've talked to you all about how that's kind of important because if your job depends on how much of this product you produce, you want to optimize it, okay? So, there's ways to think about this. I'm going to use the example of this water, all right? So here we have reactants, here we have products. They're at a nice balance initially. This is equilibrium. So at equilibrium, I'm spelling this wrong, I'm sorry. At equilibrium, your concentrations are constant and your reaction rates, both forward and reverse, are equal, okay? Concentrations, constant, reaction rates are equal, okay? That's your definition of equilibrium. Now, let's look at shifting this equilibrium. I'm going to say that I need to produce more ammonia, okay? So I might take this reaction, that's at an equilibrium, the concentrations are constant, the rates are equal, and I'm going to increase the amount of nitrogen that I put in. I'm going to put in some more nitrogen into my reaction vessel. What that's doing basically is I'm adding some reactant. I added some water to this reactant side. Which way does it shift? Well, it's going to shift to the right. It's going to be able to produce more products because you have more reactants. So this is going to shift right. So if I increase N2, it shifts to the right, shifts to the products. Now, that means that my amount of NH3 is going to increase, and that means that my amount of H2 is going to decrease, okay? H2 is getting used up to produce more of the product. It's also going to get hotter, but you won't be asked about that, okay? All right, what happens? I'm going to erase these. I'll even erase this for equilibrium. It'll save me some room. What happens if I decrease the amount of H2? When I decrease an amount, what I'm basically doing is I'm removing some water from one side of this chamber. So I'm taking some away. So I'm taking away some reactant in this case. If I was removing NH3, I'd be taking away some product. Now, in order to restore the balance, to get back to this balance that we had, some of this product has to come back over to the reactant to replace it. So this reaction is going to shift to the left. To replace the missing hydrogen. Okay, I'm going to use up, so my concentration of NH3 is going to decrease. I'm going to use up some NH3, and I'm going to produce some more N2. Okay, that is how it's going to happen. That's what's going to happen if I decrease the amount of hydrogen. All right, let's look at what happens if I increase the temperature. Temperature is going to behave the same way that temperature is going to, that's a 3. Temperature is going to behave the same way that concentrations behave. Okay. What I mean by that is if I increased my temperature, I need to find the energy term, and that's what I'm increasing. Okay, so find the energy term. The energy term's over here. I'm increasing the energy term. So I'm essentially increasing a product. Okay, so my product is essentially increasing. And it's going to spill this way. It's going to spill to the left. I'm going to have too much on the right, so I've got to spill to the left. So this is going to shift this way. What's going to happen to my concentrations is my NH3 is going to get used up because I'm shifting to the reactants, and both reactants are going to be produced. Okay? If I were to decrease temperature, this shifts to the right. Why? Because my energy term is decreasing, okay? So I'm running out of energy. I don't have enough. I need to produce more. So in order to produce more, I'm going to shift my reaction to the right, produce some more. I'm going to produce more ammonia that way. I'm going to use up some more of my reactants. Okay, so the concentrations of N2, H2 are going to decrease, NH3 increases, and energy, you won't have to worry about that, but I'm decreasing the temperature. Okay? These four processes are all about the same. The one that's weird is pressure. Okay? When you increase pressure, it's going to shift to the fewer number of moles. Fewer moles of gas only. I have 4 moles of gas on the left, and I have 2 moles of gas on the right. Erase this. 2 moles of gas on the right. So if I increase the pressure, it shifts to the right. If I decrease the pressure, it goes to more moles of gas. If I had a solid there, I would not count it. Okay? If the number of moles of gas are the same on both sides, 2 and 2, there's no shift. Okay? If moles of gas are the same on both sides, there's no shift. Finally, if I add a catalyst to this reaction, and I catalyze it with, let's say, platinum, okay, what would happen is the forward reaction rate would increase at the same rate that the reverse reaction rate would increase. So a catalyst has no effect on the equilibrium position. Okay, a catalyst has no effect. What I mean by that is shift-wise. Catalyst will not shift this reaction either direction. It'll keep it all as it was. Okay, it'll make the reaction go faster, so you still might want to add one, but it's not going to necessarily favor the products or the reactants or shift it either direction.